Hello, welcome to AP Physics 1 Unit 3. Today we'll be covering gravitational forces and interactions between massive and far objects. Now, before this unit, you learned that the force of gravity is mg, and that g is 9.8. This is true if you're on the surface of the Earth, and you're not a supermassive object. Now, what if either of those weren't true? Well, this is when g equaling 9.8 isn't really true. The one that will always hold true is force of gravity equals capital G times m2 divided by r squared. Now, what do any of these variables mean? Well, the two m's are going to be the masses of the two objects. R is going to be the distance between the centers of each object, and capital G is a gravitational constant. This is a number that you have to memorize, or if you're taking the AP exam, it will show up on the equation sheet. And the number is going to be 6.67 times 10 to the power of negative 11. Now, you'll notice that that's an extremely small number, and that's because gravitational force is what's known as a weak force, or something that only really has any influence once you become supermassive, and that's why it's such a weak force. Because everything has a gravitational force. But the reason why two people don't stick together from gravitational force is because it's too weak on people, and it's just too weak on generally big things. But once you get to planet size and supermassive sizes, that's when gravitational force has a real influence. So we can derive 9.8 in this way. Say that we have a mass m while we're on the surface of the Earth. And that means the force would equal the gravitational constant times the mass of the Earth divided by the radius of the Earth squared, and that all times the m that we are. That actually results in mass times 9.8, or mg. So if you're on the surface of the Earth and you're not too massive, this mg will always hold true, and you can use that instead. But what if our m was huge, or we were super far away so that r is huge? Those questions actually come up in the context of planets. So now let's go over some of those sample problems. Okay, so let's start off with a little simpler problem. Let's say that the radius between me and this villager is 10 meters. Well, not the radius, but the distance is 10 meters. And that the villager is 50 kilograms, and since the villager's head is a bit bigger than mine, let's say that I'm lighter at 40. Now the question is, what is the force of gravity between us? Now that would be Fg equals capital G times 50 times 40 divided by 10 squared. And that basically equals 1.334 times 10 to the negative 9. And we can see why gravity is a weak force, because this is very, very small numbers, very, very small force that, of course, me being here and the villager being here, we won't be able to feel it at all. I won't be able to feel the gravitational pull of the villager. So that's basically the reason why gravity is a weak force. It's just so tiny, and you have to get so big for any force to be non-negligible. So now we have a different problem. So let's say, obviously would not be physically possible, but let's say that I'm standing on Jupiter right now, right? And the question is, what is the force of gravity that I'm feeling from Jupiter? So let's think. The force of gravity is obviously capital G m1 m2 divided by r squared. So m1 is us, so I think we're just gonna leave m1 as is, and we're gonna say, actually no, let's say that our m1 equals 50 kilograms, and m2 would actually be the mass of Jupiter. So this is something, if it shows up on a problem, they usually give you the mass of Jupiter as a number. You don't have to remember that. So that would be the mass of Jupiter, and r, the distance between me and the source of gravity, right? Which is obviously the center of Jupiter. Now if we think, if I'm on the surface here and Jupiter, the center of Jupiter is here, r is just going to be the radius of Jupiter. That's gonna be what r is, and then all you have to do is square it. Now obviously the radius of Jupiter is also something that they'll probably give you if you get a problem like this. So if we try to solve it, Fg would equal, so the force of gravity from Jupiter would be 1295.09 newtons, assuming that I'm 50 kilograms. So we can see this number is not too much different from if it was 500 newtons if I was on Earth, right? Mainly because of the r squared being so huge in Jupiter, and the squared makes it even bigger. So we can see that the gravity of Jupiter is not too much bigger than Earth. So now we have another problem here where it's actually two situations and it's going to ask the value of one. So in this situation, the force of gravity is going to be 1.3 times 10 to the power of negative 9. Now in this situation, the force between me and the villager are 1.3 times 10 to the power of 9 newtons. And the distance between us is 10 meters. So now it's going to ask, okay, that same villager and that same person is going to stretch out into 25 meters. As you can see from this very stretched image, it's going to stretch out to 25 meters. Now there's 25 meters in between us. How much is the force of gravity between us? So this one is a bit of a, definitely can be a bit daunting, but it's actually one where you can use ratios to solve. You don't actually really need the mass for this problem. So how I do it is to just divide the equations on top of each other. So let's say you have Fg divided by, and I'll be using Fg2 as the second situation, or any 2. So we have M1, I should put M1, M2, capital G, divided by R squared, divided by G1, M2, R squared 2. So what can we see from here? Well, you're going to flip this fraction into reciprocal and then multiply it, so then we can see that all of these values cancel out. So we don't even need those values. And you're going to get Fg divided, oh, this is a bad place to write. You're going to get Fg divided by Fg2, and that equals R squared 2, since we flipped the fraction, divided by R squared. So now we have 3 variables that we know, this one, and this one. We know these 3, and we need to figure out Fg2. So all we have to do is isolate Fg2. I'm going to write it at the bottom here. Fg2 equals Fg divided by R squared 2 divided by R squared. And that equals Fg R squared divided by R squared 2. So now we can see what that answer will yield us. So plugging in the numbers, that would yield us 2.08 times 10 to the power of negative 10. So we can see that this is a smaller number than our original, which makes sense because obviously the force of gravity would be smaller if the distance is bigger. And so yeah, that's our answer. The force between us is now lowered by almost a factor of 10 actually. That's the end of the gravitational questions.